In this lecture, the main issues related to thermal comfort will be presented. The perception of thermal comfort of a person derives from the primary need to keep the temperature of the innermost parts of the body in the range 36–38 degrees C. To ensure this, it is necessary that the heat produced because of our metabolism and our activities balances the heat released into the environment. Comfort sensation derives from the unbalance or balance between the heat produced and the heat lost. So, when we are cold, it is a warning that we lose more heat than we produce, and our body is cooling down. When we are hot, we produce more than we lose, and our body is warming up. The human body not only produces heat, but also mechanical work. This is when it's walking, running, cycling, climbing, sewing, hammering, etc. The total energy produced is called the metabolic rate. Thus, the energy balance of our body can be written as M equal W plus Q, where M is the metabolic rate, W is the mechanical work, Q is the heat loss. The metabolic rate is expressed in MET, or in watt per square meter of body surface area. 1 MET is equal to 58.1 watts per square meter. A seated person produces 1 MET. As the average man has a surface of 1.8 square meters, an average seated person will produce slightly more than 100 watts. The higher is the activity level, the higher is the metabolic rate. Human body exchanges heat with the environment through convection, which depends on skin temperature, air temperature, and the speed. Radiative heat exchanges, which depend on the temperature of the skin and on the temperatures of the surfaces enclosing the space. Transpiration, which can turn into sweating, and respiration, which result into the evaporation of water with the consequent removal of heat from the skin or lungs. It depends on the relative humidity of the air. Conduction. It takes place if a part of the body is in contact with a solid object. It depends on the temperature of the skin and of the object, as well as on the thermophysical characteristics of it. Thus, the heat loss Q is given by Q equal to C plus R plus E plus H, where C is the heat loss or gain by convection, R is the heat loss or gain by radiation, E is the heat loss by evaporation, H is the heat loss or gain by conduction. Of course, the heat exchanges between the body surface and the environment depend also on the clothing we wear, as clothing acts as a thermal insulation. Thus, clothing is measured by its thermal resistance and is expressed in the unit clo. 1 clo is equal to 0.155 square meters Kelvin per watt. The value clo equal 1 corresponds to the typical winter clothing. The lowest value is clo equals 0, is a naked person. The value clo 0.5 corresponds to the typical summer clothing. Summarizing, the body heat balance, hence the thermal comfort, depends on 6 factors, of which 2 personal and 4 environmental. The personal factors are activity and clothing. The environmental factors are air temperature, air relative humidity, air relative velocity, mean radiant temperature. The mean radiant temperature deserves some more words. Consider a fire. The thermal effect of a fire on our body does not depend only on how big is the fire, but also on the distance we are from it. The closer the fire, the higher the heat flow reaching us, and the bigger we see it. If we are far away, we see the fire as a small dot, and this heating effect on us becomes negligible. Thus, with the radiant heat, the apparent size of each radiating surface must be taken into account, not only its temperature. The apparent size is measured with the so-called view factor. In order to take into account in a synthetic way this phenomenon, a specific index, the mean radiant temperature, was introduced. The mean radiant temperature is defined as the uniform temperature of an imaginary enclosure in which the radiant heat transfer from the human body is equal to the radiant heat transfer in the actual non-uniform enclosure. It is important to note that the mean radiant temperature is a function of the position at which it is measured. This is a particularly critical aspect of thermal comfort to consider in rooms with large glazed surfaces. Let's explain why with an example. Consider a room, as the one in the figure, in which 3 walls are opaque and 1 is glazed, the surface number 1. Suppose that the glazing temperature, because of the outside temperature and of the solar radiation absorbed, has a temperature of 38 degrees C, and all the other surfaces are at 26. If the person is close to the glazed surface, in that position, the mean radiant temperature is 29.1 degrees C. If instead the person is in a corner far from the glazed surface, in this other position, the mean radiant temperature is lower, 26.9. If we are in an air-conditioned environment with 60% relative humidity and negligible air movement, the only environmental parameters affecting our heat balance, thus our comfort, are air temperature and mean radiant temperature. For this reason, a synthetic comfort index has been introduced. The operative temperature, defined as the mean between air and mean radiant temperature. Going back to the previous example, if the room is air-conditioned and their temperature is 26 degrees C, the operative temperature in the two cases is respectively 27.5 and 26.5. It is evident that the person close to the glazed surface feels hotter than the other, even if their temperature is the same. To take into account this effect, the European standard EN 15251 on comfort temperatures to be maintained in heated and air-conditioned spaces refers to the operative temperature, not to the air temperature, as shown in the table, where also different categories of environmental quality required are considered. The values can be applied if relative humidity is between 30 and 70%, relative air velocity is less than 0.2 meters per second, the difference between mean radiant temperature and air temperature is less than 4 degrees C. For example, in classrooms of category 2, where sedentary activity takes place, the recommended design value of indoor operative temperature for cooling is 26 degrees C. A general index, more general than the operative temperature, as it is valid for any value of environmental and personal factors, is the PMV, predicted mean vote, according to the standard ISO 7730. The PMV model derives from thermal comfort surveys carried out on a large group of people exposed to the same environment. The survey was about their thermal sensation on a 7-point scale from cold, -3, to hot, +3. From these surveys, empirical equations were derived, capable to predict the thermal sensation in terms of PMV. In order to predict the number of people likely to feel uncomfortable in an environment, another index was introduced, the PPD, predicted percentage of dissatisfied, which provides a quantitative prediction of the number of thermally dissatisfied people. Because of individual differences, it is impossible to obtain a thermal environment satisfying everyone. Even with the PMV 0, there is always a 5% dissatisfied. In non-air-conditioned buildings, the principles of adaptive comfort can be applied, which take into account not only the purely physiological factors, but also include psychological and behavioral factors. The issue of adaptive comfort is addressed in the ANSI-ASHRAE Standard 55/2004. The standard applies the principles of the adaptive comfort in spaces without air conditioning, or when the system is turned off, and where the thermal conditions of the space are regulated primarily by the occupants through freely opening and closing windows. In these conditions, the values of operative temperature for which the environment is perceived as reasonably comfortable depend on the mean monthly outdoor air temperature. Acceptable comfort conditions are met when indoor operative temperatures are within the limits indicated in the figure. There are two sets of operative temperature limits, one for 80% acceptability and one for 90% acceptability. The 80% acceptability limits are for typical applications. The 90% limits may be used when a higher standard of thermal comfort is desired. The graph tells us that in non-air-conditioned spaces, comfort is achieved with the temperatures higher than in air-conditioned spaces. Concluding, thermal comfort is the main driver of energy consumption in buildings. The more uncomfortable is a space, the more energy is necessary to make it comfortable. For this reason, the knowledge of thermal comfort principles is crucial for designing energy-efficient buildings.